Okay. Okay. So welcome back. So someone just asked me a question, and it reminded me that I should have said something that I didn't. Is that this construction of representation on character variety is actually compatible, or more precisely functorial, with respect to inclusion. So if I have an inclusion of some surface into another, which is compatible with base point, then of course it gives me an inclusion of the fundamental group of S with respect to X into, or maybe not necessarily an inclusion, a map at least. So it's an inclusion if both surfaces have at least one boundary component. But for example, if this one is closed and this one is not, this is a surjection. But I have a map like this. So if I have a representation of that guy, I can just restrict it to a representation of that guy. So this gives me a map the other way around. Okay, so and I need this compatibility of base point, but of course, if I go to the character variety, then I don't have this dependence anymore, and I know I have a map from the character variety of S prime to the character variety of S for any choice of base point. And in particular, if I have a surface with boundary, then I can embed an annulus around the boundary. Okay, and say like if I choose a base point on the usually when I've punctured surface, I usually want to choose a base point on one of the boundary components. So in particular, it gives me a map the other way around. So a map from the character variety of that. Sorry, I want the representation variety to the representation variety of the annulus. And I claim that this map is exactly the one I described before. Okay, so this gives me, recall that this is capital G. And I claim that this map is just the map that take, a bunch of matrices and send them to the product of the commutator. So that the map I called mu before. Okay, so that was just a remark. Okay. So now let me go to the second part of this. So I want to give you a combinatorial description of character variety. So you might argue that what I explained to you before was already combinatorial, but basically it reduced everything to a bunch of copy of G. So really what I want is some description of the algebra of polynomial function on G. Okay. And I will give you not one, not two, but actually three descriptions of this algebra. And in that case, they are sort of equivalent in a fairly stupid way. So I will basically say not the same thing three times, but almost. But in the quantum case, those three descriptions will actually be interesting. So that's somehow I'm trying to set up things in a way that makes it easier to generalize to the quantum case on whatever. So of course, the first description, which is basically the definition of this affine algebraic variety structure on G, well, this is really just the algebra of polynomial in n square variable. And then you just need to invert the determinant. So really, this is a definition of GLN as, and again, as an algebraic variety. Okay, so but that's not necessarily the most convenient one. And so there is another description which is quite common in the theory of quantum group, and maybe I should put that on the web page too. It's called something an FRT presentation. So FRT is for FADF Reshetikhin, T is not ref, it's TADF, I think, something like that. So basically the idea is that So if the how should I say that? And sort of important point is that the algebra O of G and the enveloping algebra of GLN are actually dual to each other in some sense. So I don't want to too much into detail, but the idea is that those two guys are actually half algebras. So they also have a coproduct. So here the coproduct is basically given by the multiplication in G. And here the coproduct is just saying that every element here is primitive, whatever that means exactly. But it is that the multiplication here is dual to the co-multiplication here, and vice versa. And this duality pairing is just given as follows. I just take a function on G, and I take, sorry, I want to define it just for element of GLN, and then you can extend it to the whole algebra. So the idea is that this is a function on the group, but then I have the exponential map from the Lie algebra to the group. So this maps this to f of exponential of x, basically, which is a number. So that's fine. So in particular, because they are dual to each other, you have something, you have some sort of canonical element. So I have two, of course I have to be careful. So that's why I put it quote. I'm saying something which is a bit of a lie, and then I will give the precise version, because those spaces are infinite dimensional. But I can consider something like the sum of EI tensor EI in U of GLN tensor O of G. But of course, this is an infinite sum, so it doesn't really belong to this space. So if I want to make sense of that, I should take some kind of completion or whatever. But anyway, I can pick a basis of U of GLN, and then I can pick a dual basis of O of G. And the thing that although this, yeah. Yeah, but that's actually the same thing. You can use X to act on F by a differential operator, and then you evaluate at the identity. So I think that's, sorry, am I saying something wrong? Yeah, sorry, it's asking whether it's should have some differential operator. So the action, like X acting on F of some element G in the group, is like D.
Can you switch to the other board?
Yeah, sorry. Yeah, I'm trying to answer the question. Yeah, maybe I should take the derivative of f of G exponential tx, and then evaluate at 0. And I think that, sorry, 0, and then I should evaluate this at the identity, I think. And I think you just get that. Yeah, the Lie algebra acts by invariant differential operators and function on G. So I can act on a function and get another function, and then I want to evaluate the results at the identity of the group. And I think you just get, no, you're right, sorry. Okay, my bad. Yeah, you're right. This is this, which is not the same thing as what I was written before, I think. Yeah. Okay. Are you happy with that? Okay. Yeah, sure. Sorry, my mistake. Thanks for spotting that. Anyway, so long story short, you have this duality pairing. And of course, this element itself is not really well defined. But if I take finite dimensional G module, then this element actually specifies to a well-defined element in and of W tensor O of G. Okay, so basically, because this is finite dimensional, if you act with this element, then everything but a finite number of them will disappear, and then this is well defined. And one way to construct this operator directly is to observe that because of this duality, every finite dimensional G module becomes actually a module over O of G. So just by dualizing the action. Okay. And again, it's important that it's finite dimensional for this to be well defined. And I will give you a better description of this commodule structure later. But now the idea is that you have this, you have a map from W to W tensor O of G. And I can take this guy and put it on the other side at the cost of taking duality. So I claim that there is the usual isomorphism from this space to this space. This is like really just linear map. I don't mean map of module. Okay, I know this guy is just endomorphism of W, and so a map from 1 to this is just an element of that space, basically. Okay. It's just X acting on W and acting on 1 in O of G, basically. This is so yeah, I should write that. So morally, I want to say that X W is how should I say that? Yeah. It's basically like the sum of EI acting on W tensor EI, something like that. So this I look at it as an element of and of W. Does that make sense? It's a basis element of U of GLN. Sorry, I'm probably going a bit fast. So I take a finite dimensional module over G. It's quite standard that it also becomes a module for this algebra. So this canonical element, this is a basis of U of GLN. So those guys act on W. So I can just take the sum of EI acting on W, which is an endomorphism of W, tensor EI. And I claim that those guys will be 0 always except in a finite number of cases. And so this is a finite sum. Okay. Anyway. So I have this sort of canonical elements. And in particular, I can do that I can look at XV, where V is my n-dimensional vector space. So the sort of basic representation. Okay. And I claim that XV is just the sum of EIJ tensor some element AIJ, which belongs to your O of G, and this is a elementary matrix. Say again. W is just any representation, and V is like the n-dimensional representation. So yeah, I can do that for any finite dimensional representation, but somehow behind that there is the fact that the fundamental representation sort of generate all the other. So I can just write this. So Eij is the basis of endomorphism of V, so that the elementary matrices. And then I have some element of O of G here. I can just write this in this basis. And the claim here is that the Eij's are actually the same as those one. Here, sorry. The same as the definition of O of GLN. So that's the variables. O of GLN is a polynomial algebra is in n square variable. And the Aij are precisely those variables. So there are generators of. So if you like, the Aij are like the coordinate function, something that take a matrix and return the Ij coefficient, basically. So that's, I mean, the Aij are literally dual to this Eij, basically. Okay. Please check. So now, yeah, he's asking for people on Zoom. He's asking what this Eij are. This is the elementary matrices, and they are basis of endomorphism of V or GLN. Yeah. Yeah, but then I can sorry, it's confusing. When I act on some space, EI become an endomorphism of that space. And I claim that if I do that, I mean, I can choose the basis of U of GLN in such a way that they become the elementary matrices when I act on V. Of course, there is a basis of U of GLN that contains U of GLN contains the basis of GLN. Yeah. Yeah. Exactly. Yeah. Eij is the elementary matrix. Yeah. That's yeah, and so it's also a generator of O of G. Okay. And so apart from the fact that I need to invert the determinant, the only relation I have is that this Aij commute. So I will write this in a funny way, but you'll see that it's becoming. Yeah. Which is GLN in that case, because V is the n-dimensional representation. Yeah. Okay. Anyway, so basically I want to write the fact that the Aij commutes, but I want to write this in a funny way that will be useful in the quantum case. So I can, I define x1 and x2. So this will just be, let me get this right, the sum of Eij tensor identity tensor Aij. And this is the sum of the identity tensor Eij tensor Aij. And those belongs to GLN square tensor O of J. Okay. Yeah, sorry. Thanks. Indeed. Okay. So I can write that. It just so basically X, like the first leg of X, act on V. And now I want to have a version where I have like two copies of V. And X1 is the one that act on the first copy, and X2 is the one that act on the second copy. So I have Eij tensor the identity here, and here for X2 I have the identity tensor Eij. Yeah, it's just a definition. Okay. And so the sort of stupid thing that I want to write so basically I've a priori I have a bunch of relations that say that Aij commute with AKL for every IJKL. And somehow I want to pack all of that into a single relation. And then I can say that O of G is generated by just Aij, and with a relation saying that xv1, xv2 is equal to xv2, xv1. So basically, I can pack everything into a single relation. And basically, if you expand this in a basis of GLN, this will just give you all this relation of the form Aij commute with AKL. Okay. So this is really just a stupid way of sort of writing the same thing as before. But again, I hope you'll see why it's interesting in the quantum case. Okay. And of course, I also have to add the relation that I have to invert the determinant. Okay, so basically this is a presentation of O of little GLN, and this is a presentation of O of capital GLN. Algebra, yeah. I mean, this one too somehow. Except here, if you start with a commutative algebra, you don't have to put relation, but you can start with something simple. I do something more complicated where I start with like non-commutative variable Aij, non-commuting variable, and I say I want them to commute. So I can rephrase, this is just a reformulation of, this is the non-commutative algebra generated by Aij with the relation that Aij, AKL is AKL, Aij. And then again, I need to invert the determinant. Okay. So I'm just sort of stupidly giving a presentation of the free commutative algebra as a question of the free algebra by the relation that all the generators commute. Okay, and again, I'm doing that because in the quantum case it will be useful, and also because this canonical element actually plays a sort of important role. Like this is if you think of O of G as being function on the representation variety of the annulus, I don't want to be too precise about that, but more or less this guy represents the monodromy around like the generator of the fundamental group somehow. Okay, so that's a second description. So it's obviously equivalent to the first one, but just presented in a different way for now. And then the one that is probably the most useful, it's something like it's called Peter-Weyl, maybe the algebraic Peter-Weyl theorem. So basically, how like if you'd like to construct a function on G, what's a good way?
Cameras, please.
Oh, sorry. Wait. Yeah, sorry. Thanks. So somehow one good way to construct or represent a function on G is to take an element of G, act on some finite dimensional module, and take the trace. Okay, so for any finite dimensional G module W, there is a map from W dual to tensor W to O of G that takes some linear form on some vector in W And you map this to the function that map G to F of G acting on W. Basically. Okay. Oh, gosh, that's all. So really, this is just another way of saying that I'm again, this guy is actually identified with linear endomorphism of W. So I have a map from G to that by acting on W, and then I take the trace. Is that, I feel some confusion, I'm not sure. Yeah, so W dual tensor W is isomorphic as a vector space, but in fact as a G module to endomorphism, linear endomorphism. This is really linear endomorphism of W. So I can just take an element of G, it maps to a certain linear map here, and then I can take the trace. Okay. And so the first claim is that, first of all, that this is a map of G module. Okay, so W dual and W are both G module. So W is G module. So I should put it down. Where am I? Okay. W is a G module. And whenever you have a finite dimensional G module, you have an action on a dual by acting by the inverse element. Okay. And as I said before, when you take the tensor product of two G representation, you get the G representation. And it turns out that this is a map of G module when O of G is considered as G module with respect to the adjoint action. And so the statement of the theorem, I don't know, a proposition, is that actually O of G is isomorphic as a G module to the direct sum. Like the claim is that this construction is basically compatible with direct sum. Like if W is a direct sum of some module, then the maps are sums of maps basically. So this is a direct sum over all finite dimensional simple G modules of W dual tensor W. Okay. Okay. So this gives you a combinatorial description of this algebra somehow, which is internal to the category of representation of G. And of course, the isomorphism is given by this map. Okay. Any question on that? And again, I should mention that this thing is very convenient because, of course, I can do that as vector space and then check that everything is fine. But somehow, if I take this as a definition, this guy makes sense as an object in RUP G, in representation of G. Like even if I didn't know like that RUP G was a category of module, you know, whose objects are vector space with some extra structure. If it's just an abstract category, somehow this guy makes sense anyway. Somehow. So this is why this construction is interesting. And so this gives me a construction of that guy as a G module, as an object. And so what about the multiplication? And it's kind of easy to see that. Sorry, I should. Okay, let's call this. I don't know, like. Sorry, I don't know, like phi of FW. Then the product of phi of FW with F prime W prime. No, I changed. Oh, no, sorry, I didn't. I thought I did. I definitely pushed the button. It didn't. Okay, thanks. Sorry. Okay, so the product of those two guys. Well, it's really easy to see that it's just taking tensor product. Basically. Okay. So basically, this construction is multiplicative on tensor product. Okay. So now I want to write this in a fancier way. Okay. So one sort of particular feature of RUB-G. So we've seen that it's monoidal, so it has a tensor product. There is a notion of dual, and then it's actually a symmetric monoidal category, which means that the canonical map from W tensor Z to Z tensor W, that maps, that just exchanges two things, is a map of G module. Okay. And well, of course, I want to write it that way. Okay. So I represent this map that way. And so how do I write the multiplication? Well, if I want to define the multiplication, it's enough to define it on every piece like this. Or maybe even in the case where W is not necessarily a simple module, I can just take, I always have a map from W dual tensor W to O of G for any finite dimensional module. So I can just define it on pieces like that. So, sorry, I should. So this thing is included, or at least as a map to O of G, and this guy has a map to O of G. Okay. So every element of O of G is in the image of such a map. Okay. And I want to go from there to, let me get this right. Yeah. Okay. So now this guy is this guy is a G module. This is his dual. So this maps to O of D, to just one copy of O of D. Now I forget this is a tensor product. This is just a module, so I can use the map I had before. And now I just have to do something funny. So of course, W tensor Z dual is isomorphic to W dual tensor Z dual. But when you're dealing with abstract monoidal category with notion of duality, you have to switch the order. So really the canonical isomorphism is from that to Z dual tensor W dual tensor W tensor Z. Okay. Sorry, it's a lot of like combinatorial algebra, whatever, but yeah, sorry about that. So basically I want to go from here to here to define the multiplication. And I want this multiplication to be basically just the tensor product on everything around. So while there is only one natural way to do that is to use this permutation. Sorry, no, this should go there. This go there, and this goes there. Okay. So this sort of braiding that I can construct using this is a map of in RUB-G. Okay. So again, the whole point of this construction is I don't need to know that those guys are vector spaces. I can just take my category, construct this object inside my category, and I can just define this map entirely internally to my category of representation, which is kind of the whole point. And so this gives me some sort of like piecewise definition of this algebra, basically. Okay. Yeah. Any questions so far? Okay. Anyway, so with all of that, I have a combinatorial definition of O of G. And so by extension, I have a combinatorial definition of any character variety for punctured surfaces and then for closed surface by taking these quotients. I mean, I might not write it, but of course, so if you now take like an arbitrary surface with like of genus G with n puncture, then basically you have a bunch of copies of G, and you can just play this trick, but instead of having a direct sum of like tensor product of two things, you have like a bunch of things. Oh, it's clear. Like because the representation variety is just a bunch of copy of G, you can construct function on character variety exactly the same way, but then you have to take more modules, basically. I hope this was clear. Whatever. So to go from that to a description on character variety, then basically at the end of the day, as I said, you need to choose like generators of phi one, and as someone said, you can actually consider the fundamental group of it. This is sometimes more convenient, so let me give this definition. So a skeleton on some surface S. So I'm not sure it's standard terminology, but it's almost the same as a fat graph, if you know what this is, or ribbon graph, but not quite. So is a graph on S with vertices on the boundary and an order of the edges. Now the ring, maybe. At each vertex. And yeah, at some point maybe I need an orientation. Yeah, let's put everything there on an orientation on the edges. So this is one way of like combinatorially describe a surface. So I don't know if you, for the annulus, for example, you can. Oh, sorry, I forgot the most important part, such that. As deformation traps. On the graph. Okay. So again, like take some example. So of course I can do that. Usually I can always do that with just one single vertex. So for example, this is a skeleton of the annulus, and the fact that I ask the edges to be ordered at each vertex, it's because otherwise I couldn't make the difference between a disk with two holes and a punctured torus. So let me give this example. I think I want them to be actually, like that would be an house to reconstruct the surface, but I want them to be actually ordered. Yeah, yeah. Yeah, okay, so for people who don't know, Natalie is asking about the cyclic ordering versus actual ordering. You're right that the cyclic ordering is enough, but at the end of the day, I will need an actual ordering, although it doesn't really depend on it at the end of the day. And also because the vertices are on the boundary, actually, they have a linear ordering automatically, like, can start from here on. So this is a skeleton of the disk with two holes. And now the punctured torus, of course, they have the same fundamental group, which is a free group on two generators, but they are not the same surface. And I want to be able to distinguish between those. And so the punctured torus is, okay, I'm terrible at, is equivalent to something like this. And then I can do just this and this. And I should, again, it's always kind of a matter of taste whether I need to choose the orientation from the start or just put it whenever I need it. But let's say I have an orientation. So basically, what's the difference between that guy and that guy? That's precisely the ordering at the vertex. Okay. Say again? Yes, sorry. Ordering of the half edges, yeah. Okay. So this gives me a description of the fundamental group, but of course I can also do the sort of fundamental groupoid version. So I don't know, for example, it turned out to be convenient if I look at just the disk, which is fairly, of course, its character variety is kind of trivial, but actually I can do a version where I have two vertices and an edge between them, for example. So I can have several vertices. Okay. And basically so the choice of a skeleton let's say which is a graph with some extra data, that let's say a V is the set of vertices and E is a set of edges, gives an identification from between the representation variety, the fundamental with respect to, takes the representation variety of the fundamental groupoid with respect to this set of base points. Okay, so okay, so just a bunch of copy of G. Sorry, E. Yeah. Oh. Okay. So basically, every edge gives me an element of G just by the thing that represents the past, the fundamental groupoid, and I want to map it to an element of G. Okay. And then there is an action of G to the power of V on this space. And basically the idea is that at every vertex, say if I have an edge which is oriented that way, so I have a copy of G attached to this vertex, I have a copy of G attached to this edge. And let's say that in that case, G acts by right multiplication. And if it's oriented the other way, then G acts by left multiplication. Okay. And in particular, if an edge actually goes from one vertex to the same vertex, then we have an action of G by conjugation. So this work over, if you have only one vertex, then this is actually an action of one copy of G by conjugation. So you work over the definition I gave before. So again, in the case of one vertex, that's just what I was saying before, but it's actually convenient to sometimes choose several vertices. And we'll see that somehow useful when you want to glue surfaces together. Okay. Okay. Any question? Yeah, this is a definition. So the question was whether it was a definition, and the answer is yes. Well, I mean, I don't know. In a way, no, that's a claim that whenever you choose a skeleton, this gives you such an identification. Yeah, I see your point. I mean, yeah, basically you just the definition of that is that you put one copy of. I shouldn't use V 2 times. Sorry, like oh, whatever. Curly V. I don't know. So the definition of this is that you pick one copy of V for each vertex, and then every edge gives you a map between the corresponding copy of V. Yeah, I'm sorry. Yeah, I shouldn't use the same letter. Sorry, like I don't know. I don't know how to do curly V. Yeah. Yeah, sorry, that's confusing. So this is a set of vertices. So I choose this as a set of base points for a fundamental groupoid. And now we have V, which is my n-dimensional vector space. And the definition of this is basically all the way to, so I add a copy of the vector space V for each vertex. And then every pass between two vertices, I want to associate a linear map between those vector spaces. And I can do this freely because there are no relation when I have a punctured surface. What is a map of groupoid? Yeah, that's a map of groupoid, yeah. Yeah, I mean, the sort of like short definition is that it's a functor from the fundamental groupoid to the category which has object just a bunch of copy of like V basically, like many copies of V if you want. Like if you have 5 base points, take the category that has like 10 copies of V that are not equal but they are isomorphic, and give them names, and then look at functors from one to the other, I guess. Again, I mean, don't worry too much about this. Really, if you think about the case where there's only one vertex, that's definitely enough. And just believe me that there is a version for fundamental groupoid, if you're not comfortable with that. Okay. No, okay. Anyway. All right. So that was maybe painful combinatorial description. So let me switch to the topological one. Maybe you'll be relieved. the topological description. So in a way, the idea is the same, but in a sort of different way. Like something that will come up a lot is that to construct functions, we are taking traces. That's a good way to construct a function on something. So here we had like G acting on some module, and we're taking the trace of that. And here we want rather to take, well, characters, so like trace of representation of the group itself. And so basically the idea is that because a priori we start with like the fundamental group with respect to some base point, but because we are modding out by the conjugation action, we can actually forget about the base point and look at just loop in our space. Okay, so the idea is that no, I should have said that what I was saying before, it's really well defined for punctured effects. This was sort of story with graphs and stuff like that. So in the definition, I said that the vertices were on the boundary, which implies that there was a boundary in the first place, but I should have been more explicit about that. But no, S can be arbitrary. So punctured or closed, it doesn't matter. Okay. And how did I? Okay. So now the claim is that if gamma is a free loop, so again the question is how do you construct function on the character variety? And I claim that you can attach one to any free loop on S. So if gamma is a free loop on S, so by which I mean I should put it here. So I mean a loop with no choice of a base point. How do I get a function on the character variety? Well, then you can, so you arbitrarily choose a base point somewhere. Like it can be on gamma, it can be somewhere else. So let's choose it, I don't know, here. And then you can choose a path from, let's say X, from X to a point on gamma. So I don't know, something like that. Of course, this guy should have a, like this oriented. Okay. So I have a free loop, but then I can just randomly choose a base point and choose a path from that base point to my loop. And if I look at this composition, then now I have an actual path with an actual base point. So I have a loop, non-free loop, gamma tilde in pi1 of S with respect to X. So this is X. So every time, of course, there is no canonical way to do that, but I can do that. Okay. And now to this thing, I associate the function, say like phi gamma from the character variety of S to C. We just, I take a representation. So I take a point in the character variety. To be precise, I take a point in the character variety. I lift it to a representation of pi1 of S with respect to X. So I can always do that. So how should I say that? So let's say I have some equivalence class of representation in the character variety. I can lift this to a representation rho of the fundamental group based at X. Okay, I can always do that. And then to this element of the character variety, I just attach the trace of rho of gamma tilde. Okay. Okay. So I hope the way I formulate that is not too cumbersome, but that's something pretty elementary. So basically you have, your space are representation of the fundamental group. So if you have a loop, you can just apply this representation to the loop, take the trace, and because you're taking the trace and the trace is invariant by conjugation, this is indeed independent on, this does not depend on all those choices. So again, the fact that traces are invariant by conjugation is kind of, you know, the bread and butter of everything I'm doing. Okay. So for some people, he's asking whether we want S to be connected. I guess yes, because that's convenient, but you don't have to. Yeah, like the, well, yeah, it's just annoying basically. If you, like if your surface is not connected, then the, how do you define the representation variety? Again, you need at least as many base points, so you can do that. You can have a definition saying that for any, like the representation variety of a non-necessarily connected surface is by definition like representation of the fundamental group read to some set of base points having at least one element on each component, something like that. So it just deduces. It's not, there is no technicalities. And then basically this would the character variety of a disjoint union will be the direct product of the character varieties, I think. I mean, there is some kind of compatibility with disjoint union. And this will definitely be part of this TFT formulation. So I'll go back to that later, I guess. So anyway, so because you're taking the trace, you're like killing all the dependence on those choices. So this is well defined. Okay. So so basically you can let me switch bar. Maybe. Okay, and I'm almost out of time, so let me finish with that. Now you can do something else that you know if you have like several. And because I'm a mathematician, several means possibly zero. Now, if you take several loops, you can just attach to it just the product of the corresponding function. Okay. So basically, the claim is that if you do this for like one loop, what you get are like, I claim that there will be generators of this algebra function. But in fact, every function is like a linear combination of the product of things like that. So you can think of this as being the image of like some linear combination. Here I couldn't put linear combination as well. And so it allows you to define something like a universal version of the character variety, and I think Florian will be happy. So I want to call this maybe the Goldman algebra. S, which is just C, the space of C linear combination of what I want to call multiloops on S. Okay. So you just take like bunch of loops on your surface, possibly like an zero, like the empty one, and then you take formal C-linear combinations of up to homotopy, of course. I mean homotopy classes of loop. And this thing is an algebra where the product is just a disjoint union And the unit is just the empty loop. Okay. Is that okay for everyone? And so basically the claim, which I somehow already proved, is that there is an algebra map. And it's not just an algebra map, it's actually surjective. Which is somehow this is the only non-trivial part. There is a surjective algebra map from this Goldman algebra to function on the character variety. And the fact that it's surjective, it's basically equivalent to something that people call the first fundamental theorem of invariant theory. Somehow there's this very classical topical invariant theory. And one of the fundamental results basically is saying that function on the space of square matrices which are invariant by conjugation, so O of ln G invariant, this algebra is actually generated by traces of powers of matrices. So this is yeah, just a sec. And so this is how you prove that this is surjective. And again, that's only like the fact that there is an algebra map, it's kind of tautological from the construction I gave. The fact that it's surjective is not completely trivial, but it turned out to be true. Yes? Sorry. That's a very good point. So it's asking whether this is different from the polynomial algebra on the space of just one loops. And you're right, that's exactly the same thing. So because the multiplication is just given by, I was about to say that actually, because the multiplication is given by this joint union, it's really like the free commutative algebra. So this thing is a polynomial algebra. On which has one generator for every homotopy class of just loops. On loops on the surface, yeah. Indeed, this is a polynomial algebra. So in a way, its structure is actually simpler than this one. Like you should think of that as some sort of like universal version of all GLN character varieties at once. And as it often happens, it will in a way be actually simpler than this one because there is no relation. Because of course, another question which I will not answer because I'm out of time, but next time is what is the kernel of this map? And somehow this is, what Keynes theory is about, finding the kernel of that. And I guess I'll stop here. Thank you. So are there any more questions or comments? Okay. Oh. Yeah.